So now from this question we've been told, we are asked what's the mean of critical speed. So that's the critical speed of a shaft. It simply means the speed where we get the maximum amplitude of vibration. So the maximum amplitude is gotten in resonance condition where omega c is equal to omega n. So your omega c is the critical speed where and omega n is the natural angular speed. Okay, so now this second question, we're told we'll be given two diagrams. This is the first diagram, this is the second diagram. Now this is a shaft. Now this shaft has a disc attached to it at the center. So the same thing, this is still the same shaft. But the difference here is that this shaft is stationary, but this shaft is rotating. Okay, so now we've been given the speed of the shaft, we've been given the natural angular speed omega n, we've been given k, stiffness, g. This is where this entire mass of the disc is concentrated. So this is our point G here. This is also our point G. We've been given O. O is the center of the shaft. This is the shaft. Of course, these are the bearings. We have bearing here, we have bearing. The same thing, we have bearing here, we have bearing here. Now we've been given E. E is the distance between S and then G. Are you getting it? So S is the geometric center of the disc. So this is your point S and then this is your point O. Okay, while M is the mass of the disc. Now the question is, we're expected to show that Y is equals to bracket omega over omega c all squared E all over 1 minus in bracket omega over omega c squared. So we're expected to prove this. Okay, so now this is the solution. The shaft deflects in lateral direction. So when we say deflect in lateral direction, it means that the shaft deflects perpendicular to the direction of the axis. Okay, so now this is the axis. Of course, this is the shaft, and then this is the axis. So when the shaft starts rotating, we have centrifugal force acting on this disc. Okay, so now as a result of the weight of this disc, this centrifugal force tends to pull this the disc away from the axis of the shaft. So that is why, because of this centrifugal force, we are now going to have a deflection of this shaft, and that is why at this point the shaft is bending. So now the distance between here and here is the deflection as a result of the centrifugal force that has been acting on this disc. Okay, so now we have the distance between the axis and this point is what we call Y. That is the deflection. That's what we have here. But don't forget, the distance between CG, the center of gravity, and S still remains E. Okay, and we know normally that centrifugal force is given by m omega square r. Of course, r is the distance from the center of the axis. Okay, so now in this case, that implies that the centrifugal force acting here is going to be m omega square. It's going to be m omega square y plus e. So it means r, instead of r, we are having y plus e. So that means the distance here y and then plus e. Okay, now for us to have an equilibrium rotation of this shaft here, it means that the centrifugal force acting on this disc must be equal to the restoring force acting on it. It means this centrifugal force is trying to pull this disc away from the axis. That's when we have rotation. Okay, don't forget here there is no rotation. That's why I have rotating here stationary. So when we have rotation, the centrifugal force tends to pull this disc away from the axis, but this restoring force, which is ky, tends to pull it backwards. Okay, so for us to have equilibrium, that means your centrifugal force must be equal to the resisting force for complete equilibrium. Okay, so now our centrifugal force is m omega square into y plus e, while the restoring force is ky. So when we open the bracket here, we have m omega square y plus m omega square e equals ky. Okay, so now you rearrange. After rearranging, you make y the subject of your formula. So here, after making y the subject of formula, you divide the numerator by k. You can also divide the denominator by k. Okay, and that's how we have this. Okay, so don't forget k is the stiffness. So now this and this, they are the same thing. Looking at the numerator, this m omega square e over k is the same thing as omega square e slash. So this slash here is the main division line. Okay, so it's the same thing as saying omega square e divided by k over m. So that means omega square e multiplied by m over k. So you still get this back. Okay, so this and this, we're having the same thing. So here as well, don't forget, we also divided the denominator by k. So k by k, we have 1. So this by this is also the same thing as this. Look at this. So this is the main division line. Okay, so this is the same as omega square slash or divided by k over m. So, or you can say omega square times m over k. So that will give you this back. Okay, so this and this is also the same thing. Okay, so now recollect that your natural frequency is given by square root of k over m. So, or omega n square is equals k over m. So now that means instead of k over m here, we replace with omega n squared. Okay, the same thing applies there at the numerator. Instead of k over m, we replace it with omega n squared. Okay, and so we have omega square e all over what? Omega n squared. It has been replaced. The same thing over 1 minus omega square all over omega square n. Okay, so I hope it's clear. So now this means from here we are now going to get this. So all we just need to do is we open the brackets. Since square, we open the bracket and then put square. So this square is going to affect both here. The same thing here. 1 minus, open a bracket. So omega over omega n in bracket. Then you put your square outside. Okay. So now we are trying to consider critical speed. For us to have critical speed, it means the what? The critical speed of the shaft will be equal to the natural angular speed. Okay, so now since omega c is equal to omega n, so that implies that instead of omega n here, we are going to write omega c. Okay, instead of omega n here as well, we are going to write omega c, and that's why we're eventually able to have our deflection y to be equal to this. Okay, so this is what we've been asked to prove. This is what we've been asked to prove. Okay, don't forget, this is the question. The question says we're expected to prove this. Okay, and that's what we have proved.